Okay, so this might seem a little bit different because actually I'm recording this at home. It's a long story. On Friday, I forgot to hit the record button until like halfway through lecture. So just bear with me. Anyway, within the terrestrial planets, of course, we need to touch on Venus. And I don't know why that's doing that. All right. And Venus actually is more a sister planet than Mars is actually to Earth. So Venus is much more similar to size. So its cool-off rate is very similar to Earth. So actually that's why it's a little bit geologically active. We really think there's evidence of that. But the thing about Venus is, actually, we've talked about this, it has very thick atmosphere. And its thick atmosphere is full of carbon dioxide, which of course is a greenhouse gas and has made it so very hot on the surface of Venus. Those greenhouse gases actually came from the same place that we get, or carbon dioxide came from the same place that Earth's early carbon dioxide came from. That's actually from the Earth, or from the planet burping, from the internal out via like volcanic activity. So the way we know what the surface of Venus looks like actually is through having a spacecraft orbit the planet and basically map it using radar. So this is actually an example of an object on Venus. Okay, the surface of Venus actually has all sorts of these like volcanoes. Now these volcanoes are not active, and I'll kind of talk about what in a minute we believe it's Venus's geological activity looks like. So this, I think we've talked about earlier, that actually there, as far as I know, has only been one spacecraft land on the planet, and you can see that little spacecraft's foot. Isn't that adorable? So this is the surface of Venus, and it actually was a spacecraft from Soviet Union. The name of the spacecraft is Venera. Venus actually is very hot, like I said, and we're going to look at its greenhouse effect. Basically, it's a runaway greenhouse effect. So it doesn't have any hydrological cycle. It rotates very slowly. Oh my gosh, instead of 24 hours, it takes 243 days to complete one rotation on its axis. Is that not painfully slow or what? And actually, like the slide says, it rotates too slowly to generate wind. It rotates too slowly to generate that magnetosphere, or a magnetic field like the Earth's. So I mentioned that the volcanoes are dormant as far as we can tell at this point, but it looks like that Venus doesn't have plate tectonics. Instead of plate tectonics, the heat builds up under the lithosphere, builds up, and like the slide says, it's thought that Venus's lithosphere is just too strong to have fractured into plates so it can float around on its liquid mantle. So the heat builds up, and then all at once the surface melts. Is that not amazing? Every 750 million years or so, and then it, of course, cools down and re-solidifies into a crust. Is that not cool or what? And we can base that, among things, on the fact that the age of the craters. So Venus, is very reflective. It has a thick atmosphere, like I said. Now the atmosphere is full of clouds. Those clouds are actually liquid sulfuric acid. Excuse me. So Venus is very reflective. In the morning right now, fall 2015, actually, Venus is a very bright object. I think I mentioned in class, in the eastern sky in the morning. Heck, like I think maybe 4:30, 5 o'clock, 6 o'clock in the morning, you look east and you'll see a bright object, and that's Venus. So the pressure on Venus is very great. So instead of like what we say 1 atmosphere, or instead of like 13 pounds per square inch, the gas particles are so dense that actually it's 90 times that. So that's a terrible pressure to be under. Maybe that's why that spacecraft Venera didn't last very long. So yes, Venus's clouds are very reflective, and it's interesting that actually the clouds are very reflective, so that's why we see Venus shining bright in the sky. But the clouds actually act as a barrier for sunlight to get to the surface of Venus. And you would think, well, on a cloudy day, cloudy days on Earth are a lot cooler than sunny days, and there is something to be said for that. But the greenhouse effect on Venus is just makes Venus' surface so very hot. Okay, so what I mean so very hot, actually, on the Fahrenheit scale, it's running about 880 degrees Fahrenheit. Okay, now that's with the carbon dioxide. Without the carbon dioxide, it would be a negative 40 degrees Fahrenheit. So that is the influence of carbon dioxide on Venus. So to compare a little bit of Earth with Venus, if we were to take the Earth, okay, and relocate it to the location of Venus. Okay, so we're going to move it closer to the sun. Actually, we too would have basically had potentially a runaway greenhouse effect. With the warmer temperatures, we had more evaporation of that's water to go from a liquid water to a gaseous water. Now, water vapor, water gas, is also a greenhouse gas. So actually, and then in that case, we would have, this is more of the greenhouse effect, where basically sunlight comes in and interacts with the Earth's surface, and then it interacts, then it turns into infrared or heat, and that heat can't get back through the Earth's atmosphere. So the point here is that if we were to relocate the Earth, which I would suggest it, to the position in the orbit as Venus orbits the Sun, then we would be in trouble too. So a little bit about the unique features of the Earth. So the Earth actually, as we've talked about other terrestrial planets, you have a sense for, yes, the Earth is very unique. So let's kind of take a look at how unique the Earth is. And I can't help but think about the fact that in the last chapter in this unit, we're going to talk about planets orbiting other stars, and we, of course, look for a planet like the Earth. So we need these unique features on other planets for life as we know it to survive and thrive. So Earth has liquid water. Now, other planets have water. Actually, recently, Mars has been, we've actually caught water, in a sense, flowing on the surface of Mars. But Earth has abundant liquid water on its surface. And another thing about the Earth is our Earth's atmosphere has a large amount of oxygen at this point anyway. It didn't always have oxygen, and the Earth started out having one of its main components in its atmosphere was carbon dioxide. Then over the years, as the oceans formed, actually the oceans were great in providing a sink for carbon dioxide from the Earth's atmosphere, making carbonated water, right? And actually then that carbon, in the carbonated water, the animal life, plant life in particular, actually could take carbon dioxide in the oceans and via photosynthesis turn carbon dioxide into oxygen. So the oxygen, the early oxygen actually was, and oxygen today is provided by plant life. The Earth is unique in that it is both geologically active and it has this phenomenon we call plate tectonics. So the plate tectonics are, and I have a picture here to kind of remind you, the basically slabs of the lithosphere are broken up and they skate along. Skate's kind of a stretch, but they move along on the Earth's liquid mantle. So that's plate tectonics. No other planet has that. So actually up here in the upper right hand corner, I think this is a good kind of to show you a little bit about our plate tectonics. Plate tectonics has allowed basically the Earth to, what was originally basically one large landmass, to break up into the landmasses we now call continents today. So the Earth's climate is generally stable. Now, of course, if you go to different locations in the Earth, you're going to have different climates, depending upon the proximity to the equator and kind of the proximity to a large body of water in general. But our climates are generally stable, so that's important. Now, our climates are stable in a sense because our surface temperatures are really pretty stable. And our surface temperatures are stable because of our carbon dioxide in the Earth's atmosphere kind of it ebbs and flows. So carbon dioxide in the Earth's atmosphere over, hundreds of thousands of millions of years has actually kind of gone through this cycle. And so, kind of in so many words here, basically, we know that the carbon dioxide is a greenhouse gas, and so it will warm any planet, including the Earth. So in the Earth, we of course have this water cycle, and so as our surface temperatures increase, then we can potentially have more precipitation. And more precipitation, one of the things about precipitation, if you've ever, this is my precipitation, if you've ever, like, after a rain, gone out and smelled the air and you're like, oh, that air smells so fresh. Well, one of the things about precipitation is it has a scrubbing effect, and it actually does, among other things, remove particles, pollutants, but it also allows some gaseous carbon dioxide to go from the Earth's atmosphere into fall in with the rain. So of course some of the rain, a large amount of the rain, falls over oceans. So then that begins ocean water, and that's a way of basically taking carbon dioxide and putting it into our oceans or our groundwater. But in the oceans, actually, it works out well because it can be brought into the formation of rocks. It can also be brought into carbon dioxide in the Earth's oceans, as I understand it, is important gas for those little critters that have run around with shells on their backs. Okay, so they need carbon dioxide to incorporate into their skeletals, their exoskeletons. So anyway, carbon dioxide then, in that sense, do you see, is what kind of removed from the Earth's atmosphere. As the carbon dioxide is removed from the Earth's atmosphere, temperatures cool, precipitation is less, and carbon dioxide builds up. After carbon dioxide builds up, guess what? Okay, greenhouse gases increase. Carbon dioxide is a greenhouse gas. Temperatures warm, precipitation increases, and it's a cycle. Okay, so that's an important cycle.